So, welcome to what we're calling the Calculus Primer. What we're going to do here is to introduce some of the ideas of calculus in a sort of informal, learn-as-you-go kind of way, just to give you a taste of how one might really approach these ideas formally and from a more involved perspective. We're going to do something kind of basic and just to give you the idea of how these things fit together so that you may delve deeper yourself into some of these concepts. So the first thing that we need to talk about is basically slope and how we can measure and define slope for functions. So usually when we're talking about slope, you think of a line segment. So if I have a point down here, which is, let's call this x1, y1, and then I have another point over here, which is x2, y2, then clearly I can draw between these two things a line. It's a pretty decent line. And, this line is going to have a change in its y position. So this is going to be delta y, which of course is going to be y2 minus y1. And I'm going to have as well a delta x, which is going to be equal to x2 minus x1. And so if we're worried about trying to measure the slope of this line, we can write the slope of this line as the change in x over the change in y. So we can write this as delta y over delta x is equal to y2 minus y1 divided by x2 minus x1. So that's what we mean when we're talking about the slope of a line segment. And typically that's the rise of the line here, delta y, divided by the run of that segment, which is delta x. So we can do something more complicated, though, if we're talking about functions, because we can use the function. It can be any arbitrary function. It doesn't have to be a line segment. Then we can look at slopes near or even at a point. We can look at the slope of the tangent line to a function. So in order to set that up, let me draw a coordinate axis here. So this is my x-axis, this is my y-axis. And let's say that I'm looking between position x1 and x1 plus some change in x. And at x1 here, let's say I have a point P, and I have some function that passes through point P, so let's draw a function on here. So let's say that I have a function that looks like this. Okay, so I have a function, I have point P, and I have a point Q up here. And so that means that at point P, I have a function value f of x1, and at point Q, way up here, I have a function value at x1 plus delta x. So the function clearly changes value over this slope, over this curve, and so if I advance a distance delta x along the x-axis, the function will increase. So this here gives me the function value at q, which is f of x plus delta x, and this is just f of x1. And so I can also then draw a line segment between P and Q that passes through those 2 points. And clearly that has a slope, which we can write out. So let's call the slope of the line segment m. So m of our segment is going to be equal to the rise over the run of that segment, which we can now write out in terms of the values of the function. So this would be f of x1 plus delta x minus f of x1, so this is just y2 minus y1, divided by x1 plus delta x, so that's x2 in our previous parlance, minus x1. And so you can see that this is going to be equal to f of x1 plus delta x minus f of x1 divided by, since the x1s are going to cancel out in the denominator, delta x. Okay, so this sets the stage for what we're going to do next, So next what we're going to do is we're going to say, well, I'm not interested in the line in this segment slope here. What I'd really like to do is to know what the slope is of a tangent line, say right here at this point. And so in order to do that, what we're going to do is we're going to let the point P approach point Q and look and see what that does mathematically. So now let's look and see if we can calculate the slope of the tangent line at this point. As we just said, what we'd like to do is to let the points P and Q approach each other. And the formal way that we do this in calculus is, so if I want the slope of the tangent line, then I can write this as the limit as Q approaches P of the slope of my line segment, which we wrote down before. And so if I write that out, this really, so if Q approaches P, that means that delta x, this shift over, is going to become very small. So this is really the limit as delta x goes to 0 of this slope segment that I wrote down before. So that's f of x1 plus delta x minus f of x1 divided by delta x. And if our argument is correct, then whatever this expression means, mathematically, this should give us the slope of the tangent line here at this point. So this would give us m tangent. Okay, well this looks scary, but this limit is actually called the derivative. So this is, we write this as f prime at x1, and we would call this the derivative of f evaluated at x1. So it gives us the slope of the tangent line to f at x1. And so what you do when you go to calculate this, so when you calculate this limit, this funny thing, x1 is held constant and delta x is allowed to go to 0. So now you might look at this and say, well, this is crazy. I'm setting the denominator in some fraction to 0. That nothing can come of this, which is good. But let's do an example. So let's do a trivial example where I have a line and I want to calculate the slope of the line using this method. So let's say that my function f of x is just mx plus b. And so I want to evaluate this derivative over here of f at x, and so I first need to find out what f of x plus delta x looks like. So f of x plus delta x is going to be equal to m times x plus delta x plus b. Okay, so that's mx plus m delta x plus b. So the derivative then, f prime at x1 is going to be equal to the limit as delta x goes to 0. So you can think of the limit as a process. You have to slide delta x to be as small as possible. There's a formal way of describing this, of course, but we're not going to do that here. So this is my limit expression, f of x1 plus some delta x minus f at x1. And let's plug in now what these values are. So this is f of x plus delta x is mx plus m delta x plus b. And I have to subtract away from that f at x. I guess I should be putting x1s on here. So this is mx1 plus b over delta x. And so if I do the subtraction, this term cancels this one. This term cancels this one. And I'm left with m times delta x divided by delta x. So the delta x's cancel out, and so this is just equal to m. I don't even have to take the limit, because all the delta x's go away. Now, since m was the original slope of the line, this is exactly what we would have expected from calculating the slope of the line using this method. Now, that may seem like a long and arduous way of doing it, thus, but it works, and so it's not as scary as it looks. Next, I'm going to do an example using a quadratic function instead. and we'll derive some generic conclusions from that. So this time let's look and see what happens for a quadratic function. So by a quadratic function, what I mean is f of x is equal to ax squared plus bx plus c. So this implies that f of x plus delta x is going to equal a times x plus delta x squared plus b times x plus delta x plus c. And if we write all of that out, this is going to be equal to a x squared plus 2ax delta x plus a delta x squared plus bx plus b delta x plus c. No one said this would be simple. Okay, so now we want to take the derivative of this function. So we want f prime of the function evaluated at x1. And so, as we said before, this is the limit as delta x goes to 0 of f of x1 plus delta x minus f of x1 divided by delta x. So this is going to be very messy, but let's write it all out anyway. So this is equal to the limit as delta x goes to 0 of this term minus this term. So this is going to be a x1 squared plus 2ax1 delta x plus a delta x squared plus bx1 plus b delta x plus c minus ax1 squared plus minus bx1 minus c. So this is minus f at x1. All of this is divided by delta x. Okay, so now let's see what happens. So the c's cancel out, the bx1s cancel out, the ax1 squareds cancel out. And so I'm left with three terms. I'm left with the limit as delta x goes to 0 of 2a x1 delta x plus a delta x squared plus b delta x, all divided by delta x. And so I can cancel out some delta x's here. So this gives me 2a x1 plus a delta x plus b. And so now we actually get to take the limit as delta x goes to 0. The only thing that happens is that this central term, which has an a delta x, this delta x goes to 0, so this term goes to 0. So I'm left with 2a x1 plus b. So generically, since this is valid for any value of x, we can say that f prime of x is equal to 2ax plus b. And so if we compare this to f of x, which was ax squared plus bx plus c, we can see what happens. So the slope of a quadratic function looks like I basically take the exponent and bring that down and reduce the exponent by 1 for each of the terms. A constant, if this was just f of x equals c, has no slope. That's a constant, so constants go away. We also saw that in the example for the previous slide where we had a line, mx plus b, m was the slope. And so the slope if you find the slope of a function, it reduces the essentially the exponent content by 1. And so we can basically show generically that if I have a function f of x that's equal to a times x to some power, then f prime of x is going to be equal to a, since the constant stays out front, times n times x to the n minus 1. That's valid for any polynomial term. So let's see how these ideas relate back to some of the things that we talked about. So I just wrote on the previous slide that if I have some function, x, which is equal to some constant times x to some power, then the derivative, which we've up until this point written as f prime, is equal to that power times a times x to one smaller power. Now we often write, instead of f prime at x, we write derivatives as df dx. If we're taking the derivative with respect to x, which means that our limit was where delta x goes to 0, clearly I could also take limits of anything with respect to any variable. So if I have a function of time, then I could have f prime of t, or I could have df dt, which we've seen in our examples. So we saw, for example, that we wrote out that the position at any time is equal to an initial position plus an initial velocity times time plus 1/2 times the acceleration times time squared. And we wrote that velocity was equal to the change in x over the change in time. This is the average velocity, but we can find the instantaneous velocity, which is the slope of the tangent line to the position versus time curve. Instantaneous, I didn't spell that very well. Instantaneous. By writing v is equal to dx dt, that gives me the slope at a point and a slope at a point in time. Okay, so if we do that and we apply this rule, these rules up here, to this expression that we already wrote down for x, we see that the velocity, which is equal to dx dt, is going to be equal to, so this is a constant, it has no derivative. This has a 1 unit of time in it. So if this is my function of time, this is t to the 1, so this gives me 1 t to the 0, so this just gives me velocity. Here's t squared, which we just did on the previous one, so this gives me 2t, and then the 2 and the 1/2 cancel out, so this gives me v0 plus acceleration times time, which is exactly what we derived for the velocity equation previously. I can go one more down here. The acceleration, of course, is dv dt. That's my instantaneous value of the acceleration. And this, of course, comes from taking the limit of the change in velocity over the change in time. And so I can apply this again to this equation. So a is equal to dv dt. And so that again gives me nothing for a constant value. And then here's t, so this gives me 1 times t to the 0. So dv dt is just going to give me a back again. But we got that from taking the time derivative of that equation. So that shows you some idea of how these things fit in with the ideas that we've already talked about. I've gone through this very quickly, but it's just to give you a taste of how these ideas are related to the physics and the math that we've been studying.